Hello everyone, my name is Aya Salama and this is Lab 3 of Physics 2212 Circuits. First, for the introduction. So in this lab, we explore the fundamental principles surrounding DC and RC circuits. We apply concepts of energy potential as well as Kirchhoff's voltage and current laws, analyzing the behavior of the resistors in parallel and series. We use a multimeter to measure the current and potential differences, investigating the properties of our resistors and capacitors. By looking at the physical circuit and quantitative data, we gain a better understanding of the circuit's functionality and reinforces our theoretical concepts. The objective of this lab is to apply our fundamental principles to determining the current and voltage in circuits with capacitors and resistors, measuring the potential difference, and finding the time constant using data. In the first part of our experiment, we verify that the initial circuit has a current of 0.2 amps flowing through it. We then measure the potential differences across the components, finding 0.8 volts for the 47 ohm resistor and 1.9 volts for the 100 ohm resistor. We determined that the wires and the ammeters had a resistance of 0.5 ohms. In the second part of the lab, we determined that the duration of the charging phase was 15 seconds and the discharging phase was 17.3 seconds. These results are all expected considering our fundamental principles. Now for the principles of this lab. Big fundamental principles of this lab is Kirchhoff's voltage law, Kirchhoff's current law, and Ohm's law. This lab has a foundation in circuit principles, specifically Kirchhoff's voltage and current laws, as well as resistors in series and parallel. As you can see on the figure on the left, the total resistance for resistors in series and the total resistance for resistors in parallel. KVL tells us that the voltage drop across a closed loop sums up to 0. This aligns with the results in the first part of our lab where we determined the voltage drop across the resistors. We use KCL for our estimation of the current flowing through the resistors, applying Ohm's law to determine a value for current using our known voltage and resistance. Using our potential differences in current, we are able to determine resistant values for the wires and ammeters. Now let's talk about the nitty-gritty of the experiment. First part of the experiment, this was a procedure. The lab is conducted in two parts, analyzing the voltage and currents of a circuit with just resistors and then analyzing a circuit with a capacitor. In the first part of the experiment, we assembled the circuit with resistors in series, two 1.5 volt batteries, and two ammeters. We recorded the readings of the ammeter on current 1 and 2, verifying that they match our KCL value. We then convert one of the ammeters into a voltmeter and measure the potential differences across the resistors. We verified that the sum of the potential difference is equal to the voltage being put into the circuits, which is 3 volts. Then we graph the voltage against the path of the loop. Some observations we made is that we confirmed the circuit's current, taking an ammeter reading of 18.5 milliamps. We take note that by KVL, the voltage in a closed loop remains the same. For the procedure of the second part of the lab. In the second part of our experiment, we constructed a circuit with a 1F capacitor, two 1.5 volt batteries, and two light bulbs of 10 ohms and 20 ohms. In our charging phase, the circuit is comprised of the capacitor, batteries, and the 20 ohm light bulb. The capacitor is charged to the resistor and we record changes to the brightness of the light bulb over time. We do the experiment again, disconnecting the battery and replacing the light bulb with one at 20 ohms. We use the stopwatch to measure the time required for charging and discharging, allowing for a calculation of the time constant. As you can see on the figure to the right, that is an RC circuit similar to what we did in our lab, but with different resistors. For the results of our experiment. In the first part of our experiment, we confirmed the major concept of Kirchhoff's voltage and current laws. Going around the circuit path, we find no change in voltage across the B and C and a 0.8 volt drop across C and D. No change between D and E and a 1.9 voltage drop across E and F, and no change as we read the voltmeter. This sums to a potential difference of 2.7 volts, which is approximately the 3 volts supplied by the batteries. We can attribute the difference in expected and real voltage and grounding errors. So in the second part of our experiment, we look at the charging and discharging of a capacitor. In the charging case, we determine that the time for charging is 15 seconds, and it's gradually lit, and then it dims over time as the capacitor is charged. In the discharge case, we find that the light is immediately bright and goes down as power is drained from the capacitor, taking about 17.3 seconds. For a brief discussion. If we charge the capacitor with no resistor in the circuit, how quickly would our ideal model predict the capacitor to reach full charge? Will this prediction happen in real life? Then explain. If we were to charge a capacitor without a resistor in the circuit, the ideal model would predict the capacitor to reach full charge almost immediately, as soon as the closed loop is complete. Without resistance, there would be no time constant in the capacitor charging equation, meaning the voltage would rise to the initial voltage immediately. This would not happen in real life because our physical elements, such as wires, have an internal resistance that will limit the current.